Oh, gosh, what is this? Like, open. Yeah.
It's the case of you're off. So.
Yeah.
Yeah, because there's a little.
What you end up like very like
Yeah.
You know the little green one.
Look.
All right, just checking. We're not make sure.
Yeah, or,
you did. Oh yeah. Liddy, I heard of for all years. Oh yeah. Like you should be up. But this is like all like the well,
might run out.
30 years at like happy hour.
Oh.
Yeah. How about you now? Marty, good. How are you? I don't know.
Oh, just a couple. I'm not gonna go do this.
Yeah, you're gonna post your.
All right, good morning, everyone. It's 9 a.m., so we're going to go ahead and get started. Thank you all for being here for our third day, and we're joining our AGN session. Our first speaker this morning is an invited talk by Dale Kasevsky. So, Dale.
Thank you, Jan. All right, good morning, everyone. I'm going to talk today about some work we've been doing with the Sears survey, looking for AGN out to the epoch of reionization and what these systems tell us about the growth of supermassive black holes in the early universe. So one of the most debated topics in extragalactic astronomy in the last 10 to 15 years is the role that supermassive black holes and AGN play in the evolution of galaxies. We've known for some time that a correlation exists between the mass of the central black hole in galaxies and a variety of host properties, including the velocity dispersion of the central spheroid. So this is the classic M-sigma relationship. What we don't know is whether there is a causal connection that gives rise to this correlation. It's been argued that this might arise naturally just because both accretion onto the black hole and star formation relies on the same coal gas reservoirs. But we also know that hydrodynamic simulations tell us that energetic accretion events can inject energy into a system and heat up that coal gas, and that can actually regulate or even quench the star formation activity of galaxies. However, studies with HST out to moderate redshift haven't found a direct connection between elevated nuclear activity and truncated star formation activity. So this is still a very much, I think, an open question. Another open issue in AGN science is the nature of the black hole seed population and where supermassive black holes actually originated from in galaxies. There have been several formation scenarios proposed that predict a variety of seed black hole masses. This includes the collapse of a POP3 star that would lead to a light seed with masses on the order of 100 solar masses, to the direct collapse scenario where you have heavy seeds with masses on the order of 10 to the 4 or 10 to the 5 solar masses developing directly. So you have heavy mass black holes forming directly out of this direct collapse. This second scenario is thought to occur before a galaxy forms a substantial amount of its stars. And so one of the predictions here for this direct collapse scenario is that galaxies may start out with an overmassive black hole to start. And so one way that we can place constraints on the original black hole seed population is to look at black hole galaxy scaling relationships at early times and try to determine whether galaxies live above or below the local scaling relationship. And so essentially looking at early galaxies, looking at distant quasars, and trying to determine whether these galaxies have overmassive black holes or undermassive black holes, because this is one of the predictions from these two scenarios. But it turns out that not all quasars are actually well suited for this task. If you look at predictions from simulations, so this is basically offset from the local galaxy black hole scaling relationship as a function of redshift. And here, this is basically showing a variety of predictions from simulations as to how this relationship should evolve with redshift. And some simulations predict an overmassive black hole, some predict undermassive black holes. But my point here is that if you just limit yourself to bright quasars, here I'm talking about quasars with bolometric luminosities of about 10 to the 46 to 10 to the 48 ergs per second. These systems are so rare that they don't actually represent the overall black hole population well, and so you don't actually, just using this sample, you don't actually, they don't actually bear out the predictions from the simulations. But if you go to faint quasars, here we're talking about bolometric luminosities on the order 10 to the 45 to 10 to the 46 ergs per second. Now you actually start seeing that these things actually start bearing out those predictions. So this really motivates the need to search for fainter quasars, lower luminosity quasars at higher redshifts that really weren't detectable pre-JWST. So this leads me to two open questions that I want to focus on for the rest of the talk. The first is, what role do AGN play in quenching the first generation of massive passive galaxies? We know now that we are finding more massive passive galaxies at earlier redshifts or higher redshifts than we expected. And so in simulations, one of the few ways that you can produce a 10 to the 11 solar mass galaxy that is quenched 1.5 billion years after the Big Bang is to have a significant feedback event, such as AGN feedback, that will shut down that star formation relatively quickly. So the question is, do we see that borne out in the data in the last year? And the second question is, do faint quasars live above or below the local scaling relationship? What constraints can we place on the original black hole seed population, the masses of that population? So we've been trying to address both of these questions with data from the SEERS survey. Michaela Bagley gave a great summary of SEERS earlier in the week, so I'm not going to talk about the survey too much, other than to say we've got about 100 arc minutes of near-cam imaging in the extended growth strip in the EGS field, and so see the distribution there. And then overlapping that near-cam imaging, we have MIRI and near-spec R1000 spectroscopy in several of these pointings. And so just, I don't think I have to sell the power of NearCam, but I'll just point out that this source here is a redshift 3.53 X-ray detected AGN. And this is what this thing looks like in the WFC3 imaging from candles. And essentially, you could tell that maybe there's a galaxy there, but you definitely can't tell that it's a disk that has a central bulge component. And then it just beautifully comes out with NearCam when you get out to the rest frame optical. So one of the first things that we did with our near-cam imaging is cross-match our JWST detections with X-ray observations in EGS. Turns out EGS is a great field to look for AGN because it's got deep Chandra observations, 800 kiloseconds of X-ray observations, and we identified 5 sources that were at redshifts greater than 3. I'm going to apologize in advance. I've got the same cough that's going around. Try to minimize it, though. So we identified 5 sources that were well matched to our X-ray detections. One source, this guy here, EGS 532, was actually previously the X-ray emission was associated with this foreground spiral galaxy. And what we found with our near-cam imaging is that it was better aligned with this compact red spheroid sitting down here that really was basically invisible in the previous generation of candles imaging. And so this is just a montage of what these sources look like. One source is unresolved. This guy's a broadline AGN. The rest of these things, with the exception of the disk, are really bulge-dominated systems. And here you can see this little red nugget here that basically disappears, or essentially just blends in with that foreground spiral that I mentioned. So one of the things that surprised us about these, the 4 resolved hosts, is that when we perform our SED fitting, we find that they're all massive. They have masses on the order of 10 to 11 solar masses, and they have optical and near-infrared colors consistent with a quiescent or post-starburst population. So if you look at the UVJ diagram, for example, they all live in this region of a parameter space where quiescent galaxies are found. This is very different than what we found with candles at redshifts of 2 for X-ray detected AGN. At redshifts of 2, which are basically the gray points here in the background, these things are predominantly found in star-forming galaxies, and we interpreted that as being the result of, those are the galaxies that have gas that can fuel accretion events. But instead, what we're finding is as we move to higher redshifts, redshifts 3 to 5, that we're finding these sources in these massive quiescent galaxies. Now, you could argue that, well, we're just looking at the high mass end of the population, so therefore it makes sense that you're preferentially just selecting quiescent galaxies. So to try to address that, we actually constructed a control sample, a mass and redshift matched control sample of galaxies at redshifts 3 to 5. That's what's shown in these blue diamonds here. And so this plot is showing star formation rate as a function of mass. Our quiescent cut is this vertical line, or this red line here. And while we find that the X-ray AGN all live below the star-forming main sequence at redshift 4, our control galaxies are basically scattered above and below our quiescent cut. So it's not just that we're picking out massive galaxies and we're finding quiescent systems. It does look like the X-ray AGN that we're looking at here do preferentially lie below the star-forming main sequence. Now, we're not the only ones to identify AGN in massive quiescent galaxies. So this is a great spectrum that Adam Carnell showed us yesterday, actually, early in the week. And so this spectrum has these great absorption lines that really allow you to age date the stellar population. But what I love about this spectrum is this broad H-alpha emission right there. And so you're seeing basically this galaxy in the process of quenching. Remember, this is at redshift 4.7. There's not a lot of time to form a massive galaxy and then quench its star formation at this redshift. And what we're seeing is that this thing is in the process of quenching, and we see this evidence of the AGN still on there. I find this very reassuring because, as I said, in most simulations, the only way that you can produce a massive quiescent galaxy at redshift 4.7 is with the injection of energy through AGN feedback. There's not a lot of other mechanisms that can shut down star formation that quickly. And so when we find these massive quiescent galaxies at the redshifts, we're finding evidence of lingering AGN activity, which is may actually agree with that model. Now, this is obviously low number statistics, but as we get more public data in the Chandra deep fields, we're going to be able to expand this sample and see whether this holds when we include additional sources at high redshift. There's just not that many X-ray detected AGN at redshifts greater than 3 or 4. We've only got a handful in Sears, and in the deep fields we'll add another dozen or so. So that leads me to my second question. Can we place any constraints on the seed mass of these black holes? Well, to do this, we turn to our near-spec observations, our MSA observations. Fortunately, the Sears observations were split into 2 epochs. We got our imaging in the summer of last year, and then we took our spectroscopy in November. That allowed us some flexibility on target selection, so we essentially did some pre-selection based on our imaging, but we also took care to include interesting objects from the literature. And this included a candidate faint quasar that Masufusa Inoue detected. This is Sears 2782. This is a candidate low mass type 1 AGN, so that the SED of this source is shown here. This source basically looks like it has a power law SED with some strong emission lines bumping up the 356 and the 444 flux in this source. So this thing was identified, so we made sure to put a slit on it. Another galaxy of interest was Sears 746. This is a candidate massive galaxy that Ivo Lebey detected, thought to be at a redshift of 8.13, and so you can see the SED of that source here. It's got this steep red slope at long wavelengths. And so we observed both of these sources with near spec with a medium resolution grading, so this gives us spectroscopy with an R of about 1,000. And so this is the first source, Sears 2782. You can see this thing was selected to be, because it was a candidate faint quasar, and you can see essentially that point source morphology there. And here's the spectrum. You see this booming O3 line, so this really high signal and noise. And then if you look really closely at that H alpha line, see that there's a broad component superimposed onto that narrow component that has the same width as that O3 line. And so if we go back to our O3, this O3 line is detected with a higher signal and noise than our H alpha line, and yet we don't detect that broad component in O3. If this broad component was due to a galactic outflow, we would expect to see that broad component in the forbidden lines as well, and we don't. And so this led us to interpret this broad line as basically the result of a type 1 AGN, that basically we're seeing nuclear emission there. And so if we take the width of that broad line and the luminosity of H alpha, we can estimate a black hole mass, and it comes out to be about 10 to the 7 solar masses. So the full width half max here is about 2,000 kilometers per second for this source. So this may not be too surprising since this source was selected to be a faint quasar based on its photometry. But what's surprising is that this other source, Sears 746, this was selected to be a massive galaxy at redshift 8. It turned out to be at redshift 5, but then also if you look at H alpha, you see again basically this broad component superimposed onto that narrow H alpha. And excuse me. That the full width half max here is about 1,800 kilometers per second, and again we get a black hole mass of about 10 to the 7 solar masses. So again, the source is not detected. That broad feature is not detected in our O3 lines, and so the O3 lines in many of these sources is detected with higher signal to noise than H alpha, and yet we're not seeing that broad component in the O3 lines. So amazingly, these sources, if we place them on a bolometric luminosity versus black hole mass plot and put on some other sources like high redshift quasars that we knew about before JWST, these things live about 2 orders of magnitude lower than in black hole mass than typical redshift 4 to 7 quasars. And then in terms of the bolometric luminosity, about 3 orders of magnitude below the bolometric luminosity of bright quasars. In fact, these sources are more similar to that of local AGN than they are of the bright quasars that we knew about before JWST. So this just really goes to show you the sensitivity of JWST in picking up these faint systems. We also looked at the emission line ratios of these sources to see if we could identify more of them using our various emission line ratios without the broad line detections. And what we find is that if we put them up on the BPT diagram, which is shown on the left here, or the ONO diagram on the right, these sources basically fall where normal star-forming galaxies live at redshifts greater than 5. So in the local universe, AGN would be found here, and we're finding these things over here. This is not to say that this disagrees with our classification of these systems as broadline AGN. It just says that these emission line diagnostics are no longer working to disentangle AGN and star-forming galaxies at these redshifts. In fact, this is exactly where we expect to find low metallicity AGN at these redshifts. And so this tells us, the takeaway here is that the broadline detections may be one of the few ways that we can actually find these AGN. Neither of these sources is X-ray detected, despite the deep X-ray data, and we don't see emission line ratios consistent with AGN in these systems, or at least they don't separate them out from star-forming galaxies. And so the broadline detection may be one of the few ways we can actually identify this. Now, the thing I find most amazing about both of these sources is that they're not that unique. In fact, several teams have now identified dozens of broadline AGN in otherwise normal-looking galaxies. And so this is some work by Ichi Harakani doing a census of the Sears data set. This is Yorit Mathi's work, and this is Roberto Mailini's broadline AGN from the JADE survey. And so we've now got dozens of sources here where you see this broad emission feature superimposed onto H alpha or H beta in some cases. And it turns out given how many of these things are being found, you can imagine that the number densities of these things are quite high. In fact, if you look at the luminosity function, this is Yorit's luminosity function. Here's Roberto Mailini's luminosity function from his recent paper. The quasars that we knew about before JWST have a number density consistent with this orange line here. These faint broadline sources basically have a luminosity function that sits somewhere up here. This means that these sources are about 100 times more common than bright quasars, the pre-JWST bright quasar population. So there's a lot more of them. This is Eurat-Matthys number densities. Basically, that data was slightly lower resolution than the JADES and SEERS data, and so you aren't sensitive to the faintest sources. So these are a little bit brighter than the SEERS sources, and so SEERS and JADES place constraints up there. Now, back to this question about how these sources deviate or lie on the local galaxy black hole scaling relationships. One of the things we did with SEERS was basically go in and assume all the light from these sources was coming from the galaxy, from the host galaxy. We know that's not the case because most of these systems look like they're dominated by QSO emission. But for the sake of argument, let's say all the light is coming from the galaxy. That allows us to place a constraint, an upper limit on the mass of the galaxy. And so that's what I've done here. This is basically black hole mass versus galaxy mass, where I've basically these are upper limits on the host galaxies of all these broadline AGN just in SEERS. And what we find is that they basically are scattering above the local relationship, which is shown in gray here. Now, we've known for some time that bright quasars, high redshift quasars, scatter above this relationship, but this has often been thought to be the result of a selection effect, that we're just basically picking up the most extreme systems, and those systems are then just scattering above the relationship. What we're finding is that even as we push the lower masses here, we find that these faint quasars are still scattering above that local relationship. So on the surface, this appears to favor the overmassive black hole scenario. Now, this is a really quick and dirty analysis where we're using upper limits. We're not really folding in selection effects. But Fabio is going to talk to us about some recent work that he's done where all of that analysis is done, and I believe they're also finding that this favors the overmassive black hole scenario. These things are scattering above that local relationship. Now, it turns out if you push to even higher redshifts, you can find individual sources that start to place interesting constraints on the seed mass and how those seed masses grew. One of such source is this broadline AGN that Rebecca Larson identified at redshifts 8.67. You can see this plot up here. This is a great plot that Jane had produced. You can see three little clusters that fell onto our MSA slit. Here's the spectrum of the source, and if you look closely, there's H beta here, and there's another broad component, faint broad component in that H beta line. Here, again, if you calculate the black hole mass, it comes out to about 10 to the 7 solar masses. This source is at redshift 8.67, was at the time the highest redshift AGN identified and the lowest mass black hole identified at the epoch of reionization. So this is a great graphic that the folks here at Space Telescope produced for us. And so here is SEERS 1019, basically back at a redshift 8.92. And here's the other two broadline sources that SEERS identified at redshift 5.6. And so the redshift and mass of this source places interesting constraints on how this black hole formed and how it subsequently grew. And so, for example, to reach a mass of 10 to the 7 at redshift 9, this thing could have formed at a redshift of 15 as a heavy seed with a mass of on the order of 10 to the 5 solar masses, and then grew via at its Eddington limit. That's essentially what this dashed line is. And so if it grew at its maximum theoretical limit, having formed as a massive seed, you could easily explain the presence of this thing at redshift 9. If you think that light seeds are favored, well, then this pushes the formation epoch back all the way out to perhaps redshift of 20. And then even then, this source would have had to have grown via episodes of super Eddington accretion. And that's essentially what this step function is showing you. That essentially this thing had to have grown at a rate greater than what we think is the theoretical limit. So either way, this is telling us something interesting. Either the original seed mass was massive, or it had to have grown at a rate greater than what we think is possible. Right? And so it places interesting traits either way. Now, I said that this thing, when it was identified, it was the highest redshift AGN. That record has been broken twice since then. So this is it was broken once by this X-ray detected AGN in Abel 2744. You can see it's at a redshift of 10.1, and so there's an X-ray detection coincident with a near-cam galaxy. So here's that galaxy right there. And it's got some photons that make it look like it's about a 4 or 5 sigma detection superimposed on top of the X-ray emission from the cluster. And then Roberto Mailini reported high ionization lines in GNZ11 at redshift 10.6 that suggest this galaxy may also actually contain an AGN. And so I believe that the current record holder is GNZ11 at 10.6 as the highest redshift AGN. Both of these sources, if you calculate the black hole mass and the galaxy mass, again, tend to favor overmassive seeds. And these things the black holes are more massive than we would expect given the galaxy masses. Now, in the last 4 minutes I have left, I just want to highlight an interesting population that we identified in Sears. Excuse me. Two of our broadline AGN that we identified in Sears have a very strange spectral slope. So this is Sears 746. This is that source that was thought to be a massive galaxy at redshift 8. It has a really red spectral slope at long wavelengths. And then it basically flattens out, and it's got relatively blue colors at short wavelengths. This is really not how any dust law works, right? If this is a really dusty reddened galaxy, you expect additional reddening at blue wavelengths, at short wavelengths. But instead, you see what looks like to be an UV excess at these short wavelengths. And here's another example of a source that also has this blue color and then basically rapidly rises up at longer wavelengths. You could explain this SCD in two different ways. It could be a dusty galaxy, so a really massive dusty galaxy, that's what's shown in green here, with a unobscured QSO, that's the red component. Or it could be vice versa. It could be an obscured AGN causing excess emission at long wavelengths, and then a relatively unobscured galaxy at short wavelengths. But it turns out if you look at the morphology of these sources, so this is something that Elizabeth McGrath has done for us, if you look at the morphology of these sources, it's basically point-like at all wavelengths, right? And so it doesn't look like the galaxy is dominating the light at long wavelengths or short wavelengths, which you would expect. That's basically what this SCD model would predict. But in fact, the source is unresolved at all wavelengths. And so what we proposed back in our paper in February is that what we're looking at is basically an obscured quasar with a scattered dust component. So all you need is about 1 to 2% of the original QSO light to be scattered to produce this UV excess. And so one way you could do this is basically have a patchy obscuration where your direct line of sight to the nucleus is obscured, but then certain lines of sight scatter off of dust clouds and basically produce this 1 to 2% scattered light. And so this is very similar to a phenomenon I've seen in hot dog galaxies, at moderate redshifts 2 to 3. And so the Paletta template, for example, is exactly this. It is basically an obscured quasar with a small component of dust scattering. And it looks like we're seeing this in some of these broadline AGNs. So there's some of these confirmed AGN. Now, what I find most amazing about these sources is that they are quite ubiquitous in our data. In a paper that Guillermo Barro and I put out earlier this summer, this is basically, we tried to identify these sources just using a 2-color cut. And so this is 277 minus 444. Red sources at long wavelengths basically percolate to the top of this color. And this is 150 minus 200. Sources that are blue at the short wavelengths move over to the left over here. And so you can simply do a 2-color cut, 277 minus 444, 150 minus 200, and you end up finding all of these blue sources, these blue circles here, are these sources that have this flat color and this red dusty continuum. And there's a lot of these. There are 37 sources in Guillermo's paper in 100 square arc minutes. And in fact, that's using a relatively strict criteria. We've actually loosened that, and we've actually found about 75 sources in 100 square arc minutes of these things. So these broadline AGN that we're detecting in Sears and in these other data sets may actually just be tip of the iceberg, because we're finding a ton of these really dust-obscured faint quasars that look like they've got the scattered light component. So I was going to say that just to convince you guys that these things are quasars, if you look at the morphology of all of these sources, if you just do this color cut and then you look at the morphology of the sources, they are all point-like. There's not a single extended galaxy that has this unique color combination. So it does look like these things are candidate obscured quasars. All right, with that, I'll throw up my summary slide and just say that we're identifying these faint, we're identifying AGN in massive quiescent galaxies. There's basically an enhanced fraction of AGN in massive quiescent galaxies at redshifts 3 to 5. And then we're finding lots of interesting faint quasars, both through broadline detection and this unique SED spectral shape that we're seeing. And it turns out, it looks like all those broadline AGN are favoring the overmassive seed scenario. So I'll stop there and take any questions you guys might have.
Questions?
So what's the Eddington ratio for these things?
Yeah, it's a great question. You can see, so for the two sources that we identified, the Eddington ratio actually wasn't that great. It was only about 10% for the Redshift 5 sources. I believe that Rebecca Larson's source at Redshift 8 actually was basically accreting at the Eddington rate.
Oh, okay.
Yeah.
That's really helpful. Yep. The other thing is downsizing occurs when you look at X-ray statistics, and I wondered if you had any X-ray statistics now, and whether you thought this might be a consequence of downsizing, this whole phenomenon.
The fact that we're finding the X-ray sources in these massive galaxies early on. Yeah, there's still a lot to be worked out there. It could very well be that the X-ray data at those redshifts are only sensitive to the most massive galaxies, the massive black holes, and so we're picking up. That's what we tried to do control for with that control sample. But it is true that it could just be that the X-ray data is just you're not sensitive to lower mass black holes, and like I said, these broadline AGN, which are lower mass black holes, are not X-ray detected, even though one of them is unobscured, and you might expect to see it. Yeah.
Thank you.
Other questions?
Dale, great talk. Regarding those AGM feedback thing, I think you said that it's probably not surprising that you found those AGNs at very quenched, very high mass guys, right? But the flip side is, do you also find AGN on those indicative of high star formation rate objects?
Yeah, we haven't actually looked at a larger sample of X-ray detected AGN yet, but I imagine we will find them in star-forming galaxies. We see them at redshifts, out to 3. We see plenty of them in normal star-forming galaxies. And I think that even folks that are big advocates of AGN feedback will tell you that's not a problem, because not every AGN event is leading to the truncation of star formation activity. It could just be concurrent growth and things like that. So I don't know the answer. We haven't found any sources that have elevated star formation activity, like above the star forming main sequence, but we haven't actually extended that search much yet.
Well, but, do you think that the quote-unquote failure of BPN diagnostics is actually an indication of that? That actually you have very actively star-forming galaxies together with supermassive black hole?
Yes, is that a failure of the model that you'd have them?
No, what I'm saying is that actually, PVC diagram, right? So you are saying that at higher redshift, you are not going to be able to use that kind of line diagnostics to do AGN separation.
Right.
But do you think actually this actually is an indication that we are seeing both AGN activity as well as star formation activities?
Yeah, I mean, the BPT diagram won't allow you to determine uniquely whether there's an AGN in the system, but you're right. It's very likely that you're just seeing concurrent growth in many galaxies, right? In a lot of these galaxies. So this is one of our worries, right? Are these galaxies more massive than we think they are, simply because there's 20% of the light that's coming from the AGN and we don't know, right? And so I think we need spectroscopy to look for broad lines as one of the ways you could do this, since a lot of these other diagnostics don't work.
One last question here. Go ahead.
Thank you. This is really exciting. Could we use variability as a way to test the scenario that the blue excess is from this partially?
Yeah, definitely. We don't have multiple epochs for Sears, but we could get multiple epochs in other fields. Norm Grogan has been banging the variability drum for years in Sears and candles. So,
Sounds like
definitely.
a great JWST long-term variability program
that's right.
from the director.
All right, let's thank Dale one more time.
of this.
Our next speaker is Jiangwei Liu. Take it away.
Okay, good morning, everyone. I'd like to say a big thank you to the organizers for this great conference. Today, I'm very honored to introduce some very exciting results obtained with the coolest instrument on web, the MIRI instrument. Let's get started. So supermassive black holes are believed to have some kind of correlation with the host gases, and the black hole accretion can be turned on and off with the strength of active galactic nuclei or AGN change over time. This includes the intrinsic variation of the AGN barometric luminosity as well as the apparent variation of the caused by obscurations. And to get pictures of how these evolutions evolve with cosmic time, we need a complete census of the AGN phenomena. However, as summarized in the actual 2020 report, our current knowledge of AGN sensors is patchy. Notably, the highest redshift, the most heavily obscured AGN, and the lowest mass gases are poorly charted. And in this talk, I will show how MIRI brings breakthroughs in all these directions with a program called SMELS. SMELS represents the Systematic Medium Flight Instrument Legacy Astrogalactic Survey. This MIRI GTO program has targeted the central region of the good south field, including the Hubble Ultra Deep Field, with 8 MIRI filters from 5 to 26 microns with about 15 pointings. And you probably know that this field has the deepest multiversion data from the X-ray to the radio band. And we also have a large overlap with the JWST and Fresco NIRCam data. So the combination of this data set is very powerful and very wonderful for AGN science. To demonstrate how MIRI data is, here I compare it with the deepest Spitzer imaging at same field. The MIRI data does not only have much better resolution, with a much shorter exposure time, we detect way more sources. And here are the JWST NIRCam data and our SMELS MIRI field. SMELS MIRI data, and the yellow circle represents the AGNs we identified. So in contrast to the previous HST plus Spitzer errors, the NIRCam and MIRI spatial resolution are identical. This allows accurate association of sources and very good photometry data point across wavelengths. And here is the Chandra imaging and the JWLA imaging. So despite the much longer exposure time by 2 or 3 order of magnitude, many of these MIRI identified AGN are not seen. So we are using all these data sets to search AGN and benchmark the performance of MIRI. So this is our survey detection limit, and this is the redshift distribution. So in total, we detected over 3,200 galaxies with the highest spectral day above redshift 8 with photo day about 10. And this is the number of galaxy densities you can read. And we use a semi-empirical SD fitting to look for AGN evidence. There are a lot of details, but the key point is that we have realistic treatment of AGN SD variations, including emission lines. And for the galaxy dust emission, our template for normal star-forming galaxy is well tested. And we have the options to use another template for the low mass or low mass gases, which is very important right now. And here I just show you how the data looks like and how the fittings performs. And on the left-hand side, these are the dusty star-forming gases. On the right-hand side is some infrared quiescent gases without marked dark emission. And this row is NIRCam and MIRI images. And this row is observed 1D profile of the galaxy in black and the James Webb PSF in red. So you can see that the pH strengths are well traced by this photometry data, and our template for normal gases confirmed very well, and we detect quiescent gases at a wide range of redshifts, and these are some high redshift objects, redshift about 2 and redshift 3. So the data is pretty good and model things were reasonably robust. And now we can take a look at the gases with agents, and you can see right now we have much larger variation of SDs. And our model suggests this is an agent, and you can also double check the morphology to say whether the SD fitting makes sense or not. And interestingly, we also detect the lowest mass with gases with agent atoms. For example, this guy has a strong silicate absorption features. For infrared astronomer, that's a very good tracer of heavily embedded nuclear. And also this guy at redshift 2, also low mass, and it features obscured agent. And we also have very high redshift agents like this and this one. And this one is actually a confirmed fresco brown line agents in this work. Okay. I would like to point out actually the mirror now are seeing many low mass dwarf gases, and the agent selection in these systems are complicated. So for example, there is clear evidence that the gaseous infrared behaviors evolve with mentalistic. For example, you will see the pH strength reduces, and with possible change of the continual shape, okay? And for these dwarf gases, they have a hotter dust emission, which might mimic the agent colors or agent SDs, like shown in this work. And this just illustrates how a different adoption of the gaseous template may mess up the agent identification. For example, if you use a normal agent, you will find these two gases may have an obscured agent, and this one probably the agent luminosity is also high. But if you change the gaseous template to a low mentalistic gas, say feature here 11, you will find the agent evidence is gone. Okay. So actually, this one do not show any agent evidence at our other wavelengths. The only evidence is probably you are using this template saying it's agent. Well, this guy is a X-ray detected agent. Okay, so it's tricky to decide whether it's agent or not. And the takeaway message is that if we blindly applying the normal star-forming gases template to do this SD selection, you will easily find over 500 agents over the field with a distribution like this. However, there are probably a lot of false positives because you are not using the correct template. So what we did, we used the stereo mass as the approximate of this mentalistic threshold, where we believe that the change of gas infrared dust features happens. And we will pick these fittings with the normal star-forming gases template above this line, and the dwarf gases template feature here 11 for gases below this line, and pick whichever perform better around this line. Okay. So in total, we ended up with over 200 agents with a distribution like this. And here just show you the agent volumetric luminosity as a function of redshift. In total, we identify this number of agents and can be further grouped into these three categories. And this is our mirror identified agent number density. I do not want to read. Okay. And we can compare the mirror selected agent sample with some previous agent catalog, such as the Chandra Deep South agent catalog in Luo et al., as well as the pre-JWST catalog we published last year. So you can see that our shallow mirror survey with just about over 2 hours pointings yield about 2.4 times more agent than the deepest Chandra field. And about 80% of this mirror identified agent are new discoveries. And we can also break the sample into different categories. Actually, the mirror agent selection have identified over 90% of the highest redshift agent, about 80% of the dwarf agent. And the most surprisingly is actually people think, okay, since we have already super deep data from the X-ray to radio, we may have already identified all agents in massive gases, which I believe to be pretty bright. Or there are about 1/3 of the normal agents in massive gases have been picked up by mirror for the first time. Okay, so that means a lot of agents are obscured in the previous study, and we missed it. And we just combined the mirror selected agent with the agent sample selected other wavelengths within the footprint, which identified a total number about 344 agents. And this plot just shows you the performance of different techniques using a technique called upset. Basically, if you have only one dot at this line, this direction, that means the agent is only identified by this particular method. If you have two dots here, then this agent sample has identified two methods, okay, like this. So the takeaway message is that although the mirror identification is very powerful, we still have agents not identified by mirror. For example, there are some X-ray bright agents, and the total number of this mirror unidentified agent about 30%. Okay, then mirror have uniquely identified over 50% of the sample. Okay. And we did some preliminary study of the obscured agent from SD fittings, and we must say this is preliminary because we probably still miss some obscured agent because the mirror data is not super deep. And we found that actually for the heavily obscured infrared agent, there might be a trend that the obscured agent fraction evolves with agent volumetric luminosity. Also at higher redshift, it seems that half of the agent population can be called obscured. And also, we found this peculiar population of agent, which is X-ray very bright, but mid-infrared faint. And this is agent X-ray luminosity versus mid-infrared emission strength plot. Such agents are distributed here with very weak agent emission in the mid-infrared, and this shows two examples. This panel is X-ray imaging, and this is reporting the Chandra catalog. And you can look at SD, there is no trace of agent evidence. And for some systems, even if you ignore the decomposition result and think the observed flux is totally from the agent, you just cannot bring this system to around this line, okay? And we think this is probably some dust diffusion agent or agent with a boosted X-ray emission, for example, by jet, okay? And we also have more agents identified mirror, but without X-ray detections. And this plot shows agent volumetric luminosity measured from SD fitting divided by the observed X-ray luminosity as a function of agent volumetric luminosity. And this blue line shows the expected correlation for unobscured agent, and this orange line is for the Compton sink agent. So we probably have lots of Compton sink agent missed at low redshift. And for high redshift, the Chandra is detecting the very hard X-ray photons. And we probably, the obscuration is not playing a big role. And we think these agents are probably intrinsically weak in the X-ray band, possibly due to a lack of corona component in the low materialist environment. Okay, so what's the lesson here? I think the agent selection business is like a blind man and an elephant. And people have to combine all the effort to reach a complete picture. However, the real universe is more complicated than this normal elephant or the bright unobscured agent. We have lots of intrinsic variation as we see in the X-ray bright mid-infrared faint objects. And many agents are dust obscured. It's hard to say what they are. And there are way more agents with strong gaseous contamination. So that's tricky. I will leave the summary here and take questions. Thank you.
Get set up.
Really exciting. Thank you.
Yeah, thank you.
So if you look at the obscured AGN fraction plot, it looked like the obscured AGN fraction was decreasing with AGN luminosities.
Yes.
So I don't know, intuitively, I was expecting it would increase with
okay.
increasing luminosity, so I was wondering what's going on.
Yes, I think right now we didn't compensate the selection effect. And we only make a cut of those nocive massive gases with this redshift range. So probably we miss some very bright agents at bright agent as well as agent at low redshift. And but I think this trend is real, at least for this infrared obscured object, just because the near-cam data is super deep, and we have enough evidence for an obscured agent if they are not obscured at the shorter wavelengths. Yeah. But I must say this is preliminary. We probably need to combine a larger survey area to reach the final conclusion. Yeah.
Really great stuff. I have a question regarding the sources that are mirror detected but not X-ray detected. Is there any, or vice versa, is there any correlation with the morphology of the source? Do you see anything that might
in our group, there is another person studying this right now. I do not have the report. Yeah. Yeah, thank you.
All right, let's thank our speaker one more time.
Thank you.
our next speaker is Irini Lambridis.
Awesome. Is that a thing on there? All right, sit. All right. Hi, everyone. My name is Irini. Do you hear me okay? Okay, sit. So we're going to talk about the discovery of a heavily obscured radiolab AGN candidate in the Cosmos Web field. And all the AGN that we've spoken about so far, the ones that had broadline evidence of their existence, I'm going to argue that these sources, which are so obscured, you will not be seeing any broadline evidence, are not only very important, but hopefully by the end convince you that they may be the missing key towards understanding representatively what is going on with early supermassive black hole growth. So I'm not going to go into this, but I'm just going to remind you that this is the issue here, where we're trying to, with these relatively small numbers of very massive, very powerful quasars, tie them to what predictions might be for progenitor populations of their black hole seeds. And there seems to be this convergence that, a lot of people are really favoring these really heavy black hole seeds, and we have to be careful because that's actually very hard to do. To get a direct collapse black hole is really, really hard. And so if that is what our data is preferring, that's great. It gives the theorists a lot of work to do to try to explain this. But this is the consequence of us needing to really understand what's going on and looking at representative samples of AGN at these epochs, as Dale was talking about. And so this other question was this overabundance thing that people have been hearing a lot about during these talks, where there's this seemingly larger population of AGNs at these epochs than we were predicting from extrapolations at slightly lower redshifts. And the other point that I will make, did I lose? Yes. The other point that I will make is that almost all of the AGN that are going into these plots are relatively unobscured or mildly attenuated. And I'm going to put a little placeholder because I don't have the time to talk about the potential of things that are so obscured that you also can get a scattered light component, because there is a lot of discussion in that field. This is what some of Dale's objects we were talking about. There's a paper that is now live by Jenny Green talking about these little red dots and spectroscopically what we're seeing. And it's actually really complicated to really tie that together very neatly. And so we're going to ignore the scattered light potential sources as I keep talking. So, and the main thing that I also wanted to say before we move forward is I'm going to just give you a little tiny primer on what I mean by obscured. And so the unobscured sources are the really obvious broadline sources that you're seeing that are pretty consistent between their UV to their near infrared. And we are seeing a lot of evidence of these reddened AGN, or these reddened quasars. And when I say quasar, I just mean a really powerful AGN. And these are sources where you're getting preferential attenuation in the bluer wavelengths, but the AGN evidence is possible to determine from rest frame optical UV imaging. By definition, if you can see the accretion disk in the rest frame optical UV, it is not super heavily canonically obscured, barring these scattered light potential candidates. And so when I say obscured, I mean JWST is going to have a really, really hard time inferring their existence at all at these epochs, because JWST is amazing, but it's probing rest frame optical UV greater than, at these epochs that we're talking about in the epoch of reionization. And so these sources here is what I'm going to say when I say obscured AGN. And just to kind of hit the point home, for a lot of these reddened QSOs that we have found earlier that have evidence of a broadline region, when you look at these canonically very heavily obscured sources, you are just going to be seeing the ionization lines spectroscopically. And there's a lot of careful work that needs to be done to really pick out at these epochs ionization modeling on whether you can say this is due to an AGN or not. So it's a pretty complicated issue trying to find these really heavily obscured sources at these epochs. And at this point, you might be asking yourself, why do I care? Like, it's, you know, we were able to apply some obscuration correction fraction to these less obscured sources, and pre-JWST, people were feeling pretty comfortable with, it's okay for us to not get all the obscured AGN, we'll just account for it in what we expect. Problem is, recent predictions have been showing us that the majority of AGN that exist at these epochs are very heavily obscured. Not mildly attenuated, but very heavily obscured, such that if 99% of them are predicted to have column densities that you would not expect, very easy finding of them via JWST. So through simulations and through numerical arguments, this prediction of this really like unobscured quasars at these epochs are weird, pre-JWST was kind of what was being landing on in the obscured AGN community. And then this is the problem. So people were, on the lower right plot, people were really going in on this whole idea of, wow, the obscuration fractions are even higher at high redshift. So, you know, we got to be careful, guys. We're going to be missing out on a lot of AGN if we're not taking them into account. And then you have Myolino's plot on the upper right, and I tried to scale these plots together, but if there are more unobscured QSOs than we think, and the majority of obscured AGN are, you know, predicted to exist with these epochs with these fractions that they do, then there are even more obscured QSOs than we think. So this then really makes it a big, big problem right now with this overabundance of AGN. It's not even just the fact we're seeing more of these less obscured sources, but now we have to account for these sources that we're struggling to find in the first place that are also existing in even higher numbers. And this is a really big issue. You can't just start adding AGN at early epochs and be like, oh, everything's cool now, because we have lower redshift constraints. And because of that, if you just start adding AGN at the very top, you need to find some really, really clever ways to match what we're observing at redshifts that are more easily accessible through other wavelengths. So there's a lot of clever work that needs to be done to understand this. And in order to do that, we need to start finding obscured AGN at these epochs. So not all AGN have really obvious kiloparsec scale radio jets. In fact, despite how deep you go in the radio and how many cosmic epochs you probe, that seems to be about 10% of the AGN population. So the whole notion of a radio loud AGN, where you have these kiloparsec scale radio structures, is kind of a quirk of the AGN population. We're trying to understand them in the context of the broader population. But radio is less affected by the attenuation of the gas and dust in these really obscured systems, and so it can view as a beacon to finding these sources at high epochs, because we have a lot of sensitive radio information. And so pre-JWST, Brian Ensley found at this point it was the highest redshift radio loud obscured AGN in the cosmos field. And its nature was not uncovered through, you know, photometric fitting of the UV to NIR SED, but it was through the fact of its radio emission and the spectral slope of the radio points that they had. And this was really weird, because pre-JWST, finding AGN was supposed to be a really rare, hard thing to do, especially these really powerful ones. So if radio loud AGN are a small subset of the population, and that population is already a rare population, finding a powerful and powerful AGN are a rare subset of the total AGN population. Most AGN are not very powerful. They're just easier to observe. This is rare on rare on rare. It's like rare cubed. Like, this was very like serendipitous, because we found it in the cosmos field. And in this talk, we're talking about how wide area the cosmos field is, which it is relative to the other fields. But in the notion of what the expectation is of these space densities, it's actually not that big. And so there was a lot of questions that were left unsaid of whether we just got really lucky that this source happened to exist in the cosmos field, or if maybe there is an overabundance problem that we were hinting on pre-JWST. And we found another heavily obscured radio-loud AGN in the Cosmos field. This is within Cosmos Web. The QR code brings you to the archive listing. This is the highest Z candidate so far for these types of sources. It was very exciting. For us, it was the same thing where its first nature was really kind of discovered through the radio. And you expect at high redshift certain telltale signatures of what the radio information should be telling you, and that is a spectral steepening and very compact morphologies in the radio imaging. So if you're trying to go to look in your favorite field's radio data, this is one way to start doing that. And then we also will note pre-JWST, the radio information was in hand, but the photometry from the ground and the couple of space-based photometry we had was not sufficient to understand its nature. And so we also had ALMA detection of this source, but there wasn't enough points to really robustly say what the photometric redshift was and thus what the nature of it was. Well, with JWST in Cosmos Web, which has been really fantastic collaboration to be a part of, we've really been digging through the millions of galaxies, and this source was very clearly detected. We go into more details on the paper on the complexities of what you can do with this, but you put it all together to basically get a pretty well-constrained photo Z that's at around 7.6. And I will note that when you use that photometric redshift to then derive global and putting in all of our upper limits from the far infrared, our sub-millimeter points, our radio, and try to get the most robust stellar masses you can get from SED fitting, accounting for any obscuration of the star formation from dust, we get a really massive galaxy. This is near 10 to the 12 solar masses. And you may be like, that's crazy talk. And it could be. We need spectra to really confirm this. But I will leave you with that radio-loud AGN live in the most massive galaxies of their epochs for almost all of cosmic history that we've probed until this point. So would it be that weird that this one would also live in one of the most massive galaxies of its time? So this over discrepancy problem is even larger if you just blindly trust the object I found and Ryan's object. Both these objects were in the Cosmos field. They're both supposed to be the rare of the rare of the rare. We are uncovering more and more candidates every day on this. And so these sources may be evolutionarily related to the unobscured sources that we're finding at these epochs, or they may be triggered and formed from different seed models altogether. Their host galaxies may have different evolution than the unobscured sources that we're finding. We actually don't know. So we need to be looking at both these unobscured AGN and obscured sources in these epochs in order to have an idea at all what most of the AGN are doing and whether we can even use the unobscured AGN to try to say something about what most of the AGN are doing at these epochs. So I'll leave you at that. Thank you.
Questions while the next speaker comes to get set up?
Hi, thank you. Very interesting. So when you look at the measurements of the AGN luminosity functions between, say, redshift 2 to redshift 5, you have this double power law shape of the luminosity function constraints, which we don't really see in most simulations, like hydrodynamic simulations at least. So I was just wondering if that implies that there's something missing in the simulations itself, or is it obscuration at these low luminosities that is creating this flattening of the slope at low luminosities?
We're short on time, but we should chat after, because that is a very important question that has a very complex answer.
Okay. All right, any other quick questions?
It's great work, Irini. So I was thinking, if we have indeed this many dusty AGN, which I think may well be true. And given what Dale said in his talk, that some of them produce some optical light either from the AGN or from the stellar population. Aren't we going to overproduce also the Lyman continuum at these redshifts?
Yeah.
In context of Hakeem's talk yesterday,
Yeah.
that's a real concern because AGN and redshift 3 outshine the galaxies in Lyman continuum.
Yep.
So if that's also true at redshift 7, that would be really interesting. What do you make of that?
100%. It means a lot of the things we're calling AGN either may not be AGN at these epochs, or we have to come together as a field and be really open to the idea that we can't just simply extrapolate some of our knowledge and understanding of AGN from the lower Z universe to higher Z. And even our broad line, this is maybe heretical, even our broad line identification of AGN maybe needs to be deeply peeked in on how can we reproduce broad lines at these epochs and how well is that tying to known, supermassive black hole properties, because it does start giving you problems like this where we kind of break more things than is feasible.
Really neat work, though.
Okay, cool. Thank you.
All right, let's thank you one more time. Here is Fabio Capucci.
All right. Hi, everyone. I'd like to start with thanking the organizer for letting me speak today. So Dale gave an excellent introduction to the topic, so I will start from a slightly more poetic way to introduce this. So my talk today is basically about what JWST is telling us regarding the early evolution of black holes and their galaxies. After 1 year of operations of this fantastic telescope, this conference is really displaying all the beauty that we're discovering in the sky. So on Earth, beauty is often regulated by proportions, right? And similar proportions are also seen in the sky. It's been known for a long time that some properties of the host galaxy correlate with central mass, with the mass of the central black hole. And for example, one of such relations is the star, which states that approximately the stellar mass, the black hole mass is about 1,000 or 0.1% of the stellar mass of the host. So this is not always the case, of course. And for example, in a recent paper by Maiolino and collaborators, they show that recent JWST data is presenting a different picture. And in particular, what they're showing is that black holes in the high redshift universe seems to be very overmassive with respect to the stellar mass of the host, while other relations between the black hole mass and, for example, the velocity dispersion and the dynamical mass of the galaxy seem not to be violated. So this is not the first time that this was predicted or shown by the observations. About 20 years ago already, there were some papers. This is one example. They were showing that the ratio between the black hole mass and the stellar mass should evolve and increase with redshift. If you make this calculation, this is a factor of 20 at redshift 7, approximately. Also, in the pre-JWST era, there were some sporadic observations of AGN that were very overmassive at redshift 6. But now we have an explosion of observations of overmassive black holes at redshift higher than 4 with JWST. So the main questions are, is this an observational bias? Are we observing these overmassive black holes just because they're bigger, they're brighter, they're easy to observe? And of course, are the stellar masses accurately estimated? Well, since this is a JWST conference, I just wanted to spend a couple of seconds describing why we are noticing this right now in the redshift universe. Well, JWST is observing smaller supermassive black hole at redshift higher than 4, like Dale was saying before. They are fainter, they do not overshine the galaxy. So, as Dante wrote a few years ago, probably for another reason though, we are actually able to see once more the stars, measure their properties, and see that these black holes are actually very overmassive. So what we did is to, in this paper with some excellent collaborators, we executed an accurate statistical analysis of the correlations between supermassive black hole mass and the stellar mass, redshift 4 to 7. we considered observational biases, like Dale was saying, this is the main point, and compare high redshift and the local redshift and the local MM-star relations and predicting observability for high redshift black holes. This is the data set that we use. These are 23 sources from these papers. The commonalities is that they are all spectroscopically confirmed by NIRSpec between redshift 4 and 7. The black hole masses are estimated by H-alpha, and the stellar mass is also available. As you can see, they seem to be 1 to 2 order of magnitude more massive with respect to the local MM-star relation. This is from Rhines and Volonteri. Also, to note, these 4 horizontal lines here, they are the minimum black hole masses that we estimate to be observable and detectable by NIRSpec in order to get a 3 sigma detection with H-alpha. So basically, all these points needs to be above these 4 lines at the redshift between 7 and 4. I just wanted to mention that by the time that I finished this presentation, which is like yesterday, I noticed another 2 papers. One is by Mingao Yue, who is also here, and the other one is from George Rike group. I can't remember the first author now, and also Liu, which we all just talked. And they're also talking about presenting new data sets with black holes that are overmassive, and they are about 5 to 15% of the stellar mass of the Earth. So we have really a lot of observations right now. In a 10-minute talk, unfortunately, I can't go into too many details of the methodology that we use, but I wanted just to present one single slide to give you an idea of what we did. Basically, this is an MCMC approach, and we use 3 main ingredients that you can see listed here. We started as a prior as a the local relation. We considered a stellar mass function between redshift 4 and 7 to give different weights to different stellar masses in the host. And also, we consider JWST H-alpha limits in the same redshift range to take into account the fact that there is an observational bias. Overmassive black holes are easier to observe. So all these ingredients and a few more go into the likelihood function. This is a modification of the likelihood function in HOG. I don't have time to go into the details of all the terms here, but if you're interested, just ask me later. I just wanted to mention this. This is the correction term for the flux-limited survey, so the fact that it's intrinsically easier to observe overmassive black holes. So basically, all of this goes into the inference of the high redshift relation, which ends up being this. This is the main result. Basically, we find a high redshift relation that is 10 to 100 times higher than the local relation. And in particular, this is telling us that black holes plus host systems are 10 to 100 times overmassive with respect to the local relation. The standard intrinsic scatter that we find is about 0.62 dex, which is larger than the intrinsic scatter in the local relation. And also, test whether the redshift relation and the local relation are statistically different. We performed a Welch t-test. Basically, for each stellar mass, we consider the black hole mass that is predicted in the local and in the high redshift relation, and compared it with a version of the student t-test. And basically, what we find is that there is a statistically significant more than 3 sigma relation at every stellar mass. Of course, we also carefully explored the effect of the flux limit and how the bias correction term that I mentioned before influences our result. Basically, the finite sensitivity limit makes the distribution of observable sources skewed towards higher black hole masses, as we cannot observe, of course, below the sensitivity limit. And our likelihood function corrects for this bias. Now, because the JWST limit is pretty deep compared to most of the sources that we used in our paper, we do an autocorrelation test. I can give you the details later if you're interested. And basically, for the typical minimum mass that we find in our sample that is observable with NIRSpec at 3 sigma, we find that our correction is not that large. It's about 0.2 dex. So this is actually smaller than the intrinsic scatter of the relation. So we concluded that there is a flux-limited bias, of course, but this is not statistically significant in our sample. So what we are finding is actually true. So now that we have a high redshift relation from current data, of course, we can make predictions for observability of other sources. So JWST strengths, as we were finding out in this conference, resides not only in expanding the redshift universe, but also finding smaller black holes, so fainter AGN. So in these plots, we show the expected surface density of black holes whose mass is lower than the minimum mass detected so far, which is about 10 to the 6.5. So the purpose of this plot is asking how many small mass black holes we can find in current surveys. And this is calculated with the local relation, the standard Rhines and Volontieri, and the high redshift relation that we find. So as you can see, the high redshift inferred relation predicts that the distribution of smaller mass black hole peaks in a host stellar mass that is about, in log, 7.5 to 8, slightly depending on the redshift. And if you notice, this is similar to the host stellar masses than the low mass black holes discovered recently in Maiolino are detected. So our inferred high redshift relation also yields a higher value of detected black holes with small mass compared to the local relation, and we predict boosting factor of about 5 at redshift 4 and 18 at redshift 6. So the difference is more evident at higher redshift, and a search of low mass black holes in existing JWST surveys will actually be a very robust test of this relation. We also investigated the general mass distribution. This figure displays the expected surface density of black holes with a mass lower than the mass indicated in the x-axis. And our high redshift relation predicts a boosting factor of 10 at redshift 4 and 30 at redshift 6. This is for all black hole masses that are basically detected. And what is interesting, I think, is that independently on the relation, so either the local or the redshift relation, we expect that many more sources are detectable in current JWST surveys compared to what found, for example, by Arikane. They find about 8 sources in 62 square arc minute, I think. So we have yet to detect these sources, probably for 3 reasons. One, they may be inactive, of very low Eddington ratios, so a duty cycle of 1 to 10, Maiolino estimated 10 in his latest paper. The host overshines the AGN, or as Erini was saying a few minutes ago, the AGN is obscured and not immediately recognizable by line diagnostics. So to conclude, this is a slightly pictorial representation of the current black hole horizon. So the farthest black hole that can be detected with JWST so far. And blue points represent the sources that we detected, that we used in this paper. GNZ11, the farthest spectroscopically confirmed black hole. So the figure also shows a qualitative representation of heavy seeding and light seeding. As you can see, GNZ11 can be reinterpreted as an Eddington ratio evolution of a typical heavy seed, while these sources that we used, they can even be formed by a light seed, still accreting at Eddington ratios. This doesn't mean that this is the actual story. This is just a hypothesis. So to conclude, JWST allows us to reach farther in redshift and lower in mass than ever before. And I will just leave you with my conclusion slide, and I'll take your questions. Thank you.
Thank you so much, Fabio. This is so cool to see it. So have you compared to like the Z equals 1-ish relations of, M star, MBH? So pre-JWST, people were finding hints of a difference or not. How does it compare to that versus the like purely local relations.
You're talking about Z equal 1.
Yeah, yeah.
Well, there are many different versions of the MN star relation. It really depends on the sample that you're considering. If you're considering like massive galaxies, biased galaxies, etc. So redshift 1, I don't think we need version of that. It would be interesting to check it together, but what we basically used as a comparison is the Rice and Volonté relation because it was derived from H alpha, like our sample, and the stellar masses that we considered were similar. If you consider, for example, the Fourmilier-No relation, which is also like very used in the literature, the point is that that is mostly based on galaxies that are, so the black hole mass is dynamically estimated, not from H alpha. So, we consider the Rice and Volonté because it's similar to what we use.
We have a question online from James Trussler. How do these high redshift objects evolve onto the local M black hole M star relation? Do the black holes grow early and the host galaxies grow late?
Yes, so this is a very interesting question. So my interpretation, which is not necessarily correct, is that if these black holes were formed as ABCs, like we are talking about in this conference, then of course the black hole mass and the stellar mass were comparable, close to 1 at the beginning. Then what probably happened is that in these very early galaxies, stars could not form as because the black hole is rejecting them. As everything is ionized, the Jeans mass is very large, so you probably cannot form more stars. Then what happens is that at some point, exhausting all the gas that can start to slow down its growth. And then, the galaxy maybe merges with other galaxies, adds a lot of mass, and then the black hole is evolving probably mostly horizontally. So it starts like very above, then it stops growing, the black hole, and the system moves horizontally because it's just adding more mass, stellar mass, and not much black hole mass. But this is just my interpretation.
First more questions because we have a technical difficulty. So we can log into this laptop log us in and we'll ask questions and answer.
Very interesting results. I'm wondering whether you or someone else who is working on this considered constraints from low redshift, from software X-ray background that was measured by Chandra, because like these large quantities of black holes at high redshift should emit hard X-ray emission, which should be shifted to soft X-ray. I wonder if somebody considers like whether any of these measurements are emulating the soft X-ray background with it.
This is very interesting. I haven't personally done it, but I agree it's something to check. So I don't have an immediate answer to that.
Thank you for the nice talk. I wonder if you could comment on how reliable the stellar mass estimates are at high redshift. Is there combination, for example, by the
Yes. So this is, as I mentioned in one of my slides, this is a very important question because if the stellar masses are wrong by like 2 orders of magnitude, we shouldn't be talking about overmassive black holes. But there are several reasons to think that they are not that wrong. Okay. So the reason is that, as I think Majolino was making that discussion, even if all the light that we observe comes actually from the stars, there is no AGN contribution, then it's the stellar mass of those wouldn't change by more than a factor of 5 or so. So it's still like 2, maybe a factor, like more than an order of magnitude above the MN stellar. So even if all the light would come from stars, that wouldn't change much the relation. So the other reason is that, so when we were doing this, can I still talk? Yeah? Okay. Yeah, so when we did this test, we actually made a sanity check, okay? So we started from the local relation, like the rise and volunteering, okay? And we generated, like randomly, 23 sources, like the ones that we investigated in this paper, okay? Considering stellar mass function, so lower mass systems are more likely than higher mass system, considering the JWST limits in H alpha, okay? So we generated 1 billion 23 systems, okay? And we wanted to count how many of these 23 groups would fall in a rectangle that is within basically the area observed by the 23 sources that I showed. And out of 1 billion, there is not a single one, not a single group that falls there, okay? Instead, if you use like a higher redshift relation that we found, a lot, I don't remember exactly the number now, but a lot of them would actually fall there. So this is just a little game that we made with a student, but this is something to think about. If you start from the local relation, even if you consider all the JWST limits in H alpha, there is no way you can reproduce that sources. And, even if not a single one in a billion. So even if the stellar mass is wrong by a factor 5 to 10, it would be very difficult to reproduce that distribution of sources.
One more back. We're almost back up.
Okay, so thank you for your very nice talk. I was wondering about the bias effect estimation, because you inserted the bias estimation into the likelihood. So I was wondering if you also applied like a non-parametric method on the whole sample of the distribution versus redshift to estimate the limiting luminosity, let's say, of this sample, and this can be done also with the Efron Petrosian method. And if you compare these results with your estimation of the bias from the likelihood maximization.
Yes. So we didn't use a non-parametric methods. We only used parametric methods. But what we did to test what we found is not to consider the local relation as a prior. Okay. In one of the slides, I showed that the prior that we used is the local relation. Okay, so we were thinking, okay, this is starting from the local relation and it's maybe just shifting in a statistically insignificant way the thing above. But even if you don't start from the prior, you don't consider a prior as a local relation, the final relation that you get is actually very similar to the one that we started with. So we did not use any non-parametric methods, only parametric methods, but we actually removed some of the priors and the results are very similar.
Okay, thank you.
Thank you all. Let's thank Fabio one more time. Now move on to the last speaker of the session. Final speaker is Yuzo Ichikawa. There's a card here, and I'll give you a 2-minute.
Okay. Can everyone hear me? Hello? Are we all good? Hello? Can you hear me? Okay, thank you. My name is Yuzo Ichikawa. I'm a graduate student here at Johns Hopkins University, so thank you for inviting me to this talk. I want to share our quick results from our Cycle 1 program looking at adult quasar. And so, as you've heard from all the previous talks, JWST has been pushing a lot of our understanding and maybe posing more questions about supermassive black holes, galaxies. So I want to bring it back up a little bit to studying system at cosmic 2, so we're talking about redshift 2 to 3, where we have an elevated system with high star formation, large galaxy formation, and also high quasar activity. So we think this is a pretty nice epoch where we have large interactions like mergers, as you might guess. to give us a good insight about what we've been talking about co-evolution and all that, using a case study with dual quasars. So I'm going to quickly define what a dual quasar is. So we have two supermassive black holes rapidly accreting, they're very luminous, but they're at like kiloparsec scale distances. They're not quite gravitationally bound as binaries yet. So we're at this regime where we're still interacting with the galaxy. So when Cookie introduced our team, Nadia Lukansky is my advisor here, so I want to thank everyone. So it's going to be a little bit more intro heavy because it's a fairly new topic in this field. So I want to put everything in context as I talk about our target. So when we have galaxy mergers, I'm not really going to talk about how these quasars are. Let's assume these quasars exist. They emerge. As they get into a merger, they're going to slowly interact and hit this regime where in this galactic scale, kiloparsec scale, as they slowly inspire through dynamical friction, and then maybe we'll hit this parsec regime, they get into a binary, maybe merge, and we have a massive supermassive black hole. Hopefully someone can solve the final parsec problem, but all of this, we have a lot of unknowns. We don't really know the whole process from large scale all the way to the small scales. So our real goal is to really capture the evolution of different snapshots, find a bunch of these targets and really study them in detail. So as we do this, we're going to be talking about kind of the basic. I'm not going to, we've already heard enough about the main questions of quasar evolution. But then there's also these new questions about how do dual quasars form? What do they interact? How do they interact with the galaxies? What are the host galaxies like? And as our group, one of our main goals is to study the host galaxies, the dynamics, the gas dynamics through using integral field spectroscopy to really study the galaxy and black hole interaction as best as we can. And so there we go. Just in context, there's been a lot of papers out. Simulations do show we can get even up to 3 quasars interacting. It's kind of crazy, and there is actually some candidates our postdoc is working on. And there is a GTO program that did look at the 20 kiloparsec scale separation at redshift 3. So there are some, people working on these objects. But the danger is you might end up with a lens quasar. We have 2 identical looking quasars, and they did a lot of follow-ups only to find out that there's a host lensing foreground. So it's really frustrating. And so I want to make the pitch that the type of target I'm going to be talking about is in this small sub-arcsecond regime. And a lot of these red dots is filled out by our group. It's obviously a lot easier to find dual quasars when it's closer to us, and when it's farther away, it's easier to find larger separation. So hopefully going to fill in this gap and understanding a little bit more about the evolution cycle. So how to find them? We use a special technique using Gaia. So let's say there's 2 quasars. We have Gaia, but Gaia doesn't resolve everything under 1 arcsecond. So we can use this cool technique called varstometry, where we look at the variable fluxes on the 2 quasars. So what Gaia would see is just a single source that's flickering because of the unsynchronized flux variations. And what that translates to is not only a flux variation, but also a shift in the center. So they call them astrometric jitter, which we think corresponds to an actual physical separation. And so when we do that, we can systematically find a whole bunch of these candidates. And then we use Hubble to do follow-ups and confirm that they are indeed pairs. And then we pick out our favorites for our JWST studies. We pick out 2 at redshift 3 and redshift 2 here. And we're only just getting the tip of the iceberg. And so I'm going to talk about one of the targets at redshift 2. So this is 0749. We did a lot of follow-up studies with radio and split spectroscopy with Gemini, and we're confident that these are actually 2 quasars, not like a star and quasar superposition, and with some analysis of the imaging, we think that there's a host galaxy, but we're not really sure. So our goal is to confirm all this
and answer, is it really a dual quasar? Is it not a lens? And what is the host galaxy doing? And already with the near-spec and MIRI IFU, today I'm just going to talk about a near-spec since I don't have a lot of time. We can already see the extended emission from the host galaxies for both of these targets. So that's really great, and it really just highlights the power of interlocal field spectroscopy for JWST. So hopefully we can get more usage out of it and study this in detail. Now, how do we study the host galaxy behind these bright quasars? Well, we need to remove the quasar light because the quasar is going to be outshining the host galaxy. So I'm also part of the early release science program where we developed a software that basically removes the quasar TSF structurally, and then we can extract the host galaxy, get the nice surface brightness and velocity maps to great detail. And we can do this up to quasar redshift 3. We haven't done it at higher redshift. The higher redshift things we can do. So that means we can also do with our dual quasar. Now remember, we have 2 quasars. We have 2 TSS, which is a real pain. But we think we are actually seeing extended host galaxy reaching almost several kiloparsecs. And we do recover some of those tidal field features that we were sort of hinting from the HST emission. And we haven't, I know this isn't a great image, and we haven't done some single noise tests to get rid of the outside regions, but it is pretty fluffy. But one of the biggest surprises corresponded velocity map. We can actually see a really nice rotation field, but it looks like a really big rotating disk, which is not what we expected to find in an SU merger. So we're like, what is going on? So we came up with 2 ideas. Either this is a merger and this looks like this, and there are some paper that says just from kinematics, you can't really pinpoint the merger. Okay, but what if it is a giant disk and you have 2 quasars? How do you end up with that? So we've been playing around with some ideas that there are some simulations that show you could have this fragmentation forming 2 massive black holes, up to like black hole masses that tend to be 6 and above. So it's a crazy thing. So we solved this and we're like, okay, we need to go back to the quasar structure. And then, so we just extract the central apertures from the 2 quasars, and we actually see a very similar looking quasars. So this is the red one is the bright quasar, and then the blue one is the faint quasar. In some papers, we just say, that's a lens, we're done. But if you compare the emission lines and of the spectrum, we do see differences. There are velocity offsets. The line profiles are ever so slightly different, line ratios, but everything else looks very similar. Line ratios, strong iron emission everywhere. So this was, we have two weird questions. Weird rotating galaxy disk, maybe, and 2 really weird looking quasars. So we're like, okay, is this a merger? We're not sure. Is this like disk fragmentation events? Maybe. But another one, we're like, okay, maybe we have 2 quasars that are treating very similarly. Is it interacting with each other? Is it maybe just eating the same gas? And if it's due to a merger, it needs to be that we start with 2 galaxies with the same gas content, treating in the same way, merging into 1 galaxy, which is weird. Or we have a merger and then it's just ending up eating the same type of gas. So we don't think it's a lens. So here's all these cases we built up. But the takeaway is like we had this weird merger maybe event with maybe similar quasar rotation. So we think that this, we're not sure if this target is a representation of the physics that's happening when we have 2 quasars at small distances, or it's just a unique population for quasars. We just don't have that many out there. And in the title I mentioned ALMA. We got some ALMA observations looking at the molecular gas in this target. It's important so we can see the field content that's feeding the star formation in the quasars. And we do see very clumpy gas structures, maybe a little bit filamentary connecting the 2 quasars. We're looking at this in more detail, but the rotation matches the H alpha emission and actually the other emission. So it is fairly consistent, but we do have more questions than real answers about it. So I just want to quickly end it. Papers are coming, but the main takeaway is that we can find these dual quasar candidates, and maybe hopefully I can invite you excited about dual quasars as another set of population of quasars to study. And we do have one that's fairly weird. Maybe you don't think it's weird, but and we'll have more in cycle 2, and maybe we should get more things this week. Thank you very much.
Hi, I'm Mason Ruby from this great talk. I was just wondering if this is a merger, what's this that the quasars have all in the in spiral and along the time scale?
Yeah, that's a great question. We're not quite sure where to pinpoint the merger stage. So we're still looking into the galaxy dynamic mission. So, but yeah, the H alpha is too frequent with the fair. We do see some, that's a really good point.
Hi, thank you for the fascinating talk. This is Minghao Yue from MIT. So I have a few questions about the velocity fields. So I see the velocity fields from the near spec IFS, where the two quasars seems to be, it's kind of counterintuitive. I feel like the two quasars should have like, the axis should be aligned the other direction, right? They should one have in the red region and the other in the blue region. Should that be more intuitive? And I'm wondering, what does the velocity field look like in your ALMA image? Since you have the old 4 to 3, right?
Yeah.
Do you have the same pattern here? And also, I was wondering, like in the ALMA image, can you see the velocity difference between the two quasars? That would be helpful to distinguish the lensing and dual quasar scenario, I think.
Okay, thank you for the question. A lot of good questions. So I'll start with the velocity fields in ALMA. Yes, we do also see the velocity quasars, so that's another, we don't think it's a lens. And also the velocity, the field seen in near spec and ALMA, they're also quite similar. So we're seeing, velocity, from, where's my pointer? From the reddest side to the bluest side, we're seeing differences of up to several hundred kilometers per second. So it is quite, it's massive rotating. The structure is slightly different. Maybe it's a little difficult to see from this image, but we do see that. I will need to double check, but the velocity fields do sort of match with ALMA too, with this just structure. So maybe at least with H alpha, we're seeing the star formation streams. We're not quite sure yet. So that's something we're trying to look into.
Let's thank you one more time. Thank you to all the speakers in this morning's session. Since we're a little bit behind, we're going to come back from the coffee break 5 minutes later. So we'll start the next session at 11:05.